So the Earth isn't actually round, and perhaps, living in a place like Vancouver, maybe a lot of us know this. If you live on the prairies, maybe you think it is. But yeah, the Earth is not actually round. There are numerous reasons that there are distortions from an idealized sphere. So actually, the largest distortion, which we are not, consciously aware of as humans just walking around on the planet, the Earth is actually 43 kilometers wider at the equator than it is between the poles, and this is due to the Earth's rotation and centrifugal force stretching it out. Then there's topography, which causes undulations on the Earth's surface, and if you were to take away the oceans, there's about 20 kilometers of difference in elevation between the lowest point, the Marianas Trench, and Mount Everest. And then on top of that, the most recently discovered, there's actually gravity differences due to density differentials inside the Earth's crust, which also causes undulations at a much smaller scale, about 180 meters. But we'll talk about all three of those and why we have to think about each of those in order to actually condense and simplify the Earth to represent it. So the largest contributor to the distortions from an idealized sphere is centrifugal force. So the Earth's rotation causes it to bulge at the equator. And so the diameter between the poles is actually 43 kilometers less than at the equator, or 99.7%. So the Earth is essentially only 99.7% a sphere. And these differences are much larger than topographic or gravity-induced differences, and they happen on a global scale. So the shape of the Earth is actually much closer to what's known as an oblate spheroid. And we can fit an oblate spheroid, so that's a three-dimensional ellipse, to the Earth, but topography and gravity differences must be dealt with separately. So just to highlight a little bit about what an oblate spheroid is, I've just created a little Python code sort of highlight the differences between these shapes. So just a little bit of geometry. Hopefully you all are familiar with the differences between a circle and an ellipse. So a circle is a two-dimensional object that is perfectly round. All points along its circumference are equidistant from its center. An ellipse, on the other hand, is wider or taller than it is in the other direction. So in this case, it's wider than it is high. And so moving into 3 dimensions, we have a sphere and then an ellipsoid or an oblate spheroid. They can be used essentially interchangeably, right? And so a sphere is perfectly round in 3 dimensions. An oblate spheroid is not. It's more of like a squished ball. So it's wider than it is tall, for instance. And so looking at this at the scale of the Earth, this illustration is a cross-section of a perfect sphere and a cross-section of an oblate spheroid. It's really hard to really notice any difference at all. You can notice maybe it's a little bit wider. But if we zoom in, you can see at the equator, there is actually considerably more difference than at the poles. And so the deviation from an idealized sphere is greatest at the equator, where the Earth's rotation is fastest and centrifugal force is greatest. So just another view of that, right? If you want to amplify that by 10 or 100 times to just get more of an idea of what's going on. And so we can display this at the Earth's scale. So the gray lines are an idealized sphere, and the red lines are an oblate spheroid. And at the scale of the Earth, it doesn't seem to make that much of a difference if you're looking at the whole planet altogether. But nonetheless, it is important. Again, there's 43 kilometers difference between the sphere and the spheroid. But you can exaggerate that a little bit and see, again, how these shapes actually compare. Again, the gray, black is a perfect sphere, and the lighter color is an oblate spheroid. So we can fit a spheroid to the Earth, but we also have to deal with topography and gravity differences to get the most accurate representation. Topography gives the Earth's surface an irregular shape. Topography gives the Earth's surface an irregular shape. And at local scales, that can be really, really intense, right? So like the city of Vancouver, we see the North Shore Mountains. They're this big, imposing rock feature that causes a lot of vertical relief in a fairly short distance. But at the global scale, it essentially smooths out. And we don't really need to worry about it unless elevation is a specific component of what we're working with. So we can essentially just smooth out and ignore topography and then use additional data to account for it when we need and ignore it when we don't. So depending on the type of map you're making, topography may or may not be important. And so here you actually see an illustration of the shape of the Earth. And so I have Mount Chimborazo in Ecuador on here because despite Mount Everest being the highest point above sea level on Earth at over 8,000 meters, this mountain is actually the farthest away from the center of the Earth. So if you go to the top of this mountain, you are farther away from the center of the Earth than you are if you go to the summit of Mount Everest. And the reason for that is this mountain is located right on the equator. So it's on that equatorial bulge. So in addition to the centrifugal force pushing the land surface there outwards, it's a 6,200 meter high volcano. And so that is actually the farthest point from the center. It's kind of interesting fun fact for the day. Now, in addition to topography, we have density and gravity differentials due to changes in the composition of the Earth's crust. So certain portions of the Earth's crust and mantle are actually heavier because they have a different composition than other portions are. And so those heavier portions pull the Earth's surface down lower. So we have like a low point underneath of southern India, for instance, because the crust there is heavier. And then we have less dense regions. So for instance, in the North Atlantic, which allows the crust to rebound and come up. And so the differences here are only on the scale of about 180 some odd meters. But these differences are continental undulation. They're continental scale in undulations. So they do need to be accounted for. And we have to think about that when we fit the ellipsoid to the Earth. So we can ignore topography and just account for it when needed on a local scale. But we have to account for these differences due to density.